Hi guys, so before talking about resonance, let's look back at the conservation of energy. So there was a whole lecture about that, but let's take the example of the spring again, horizontal spring, and you see how energy is switching back and forth between kinetic energy and elastic potential energy. So you pull your spring, everything is in the elastic potential energy, and then you let go. So you're going to have a little bit of both. When it's going through its equilibrium position, it's going to be all kinetic. And then again, it's going to be squeezed here. So it's going to be elastic potential energy and so forth and so on. So now if we use what we did the last lecture, here, if we use what we did the last lecture, you see that we said that the displacement, and it should be a y. No, it's a x. It's x. So it's going to be the amplitude cosine omega t. Let's say there's a phase here. It depends when you start your stopwatch. And then you have the velocity here, which is you take the derivative. And here you have a sine. And you have the acceleration. Now, if you look at the kinetic energy, so kinetic energy, it's going to, at a given time, so 1/2 mv square, and we neglect friction, we neglect damping, so it would keep going back and forth forever. So the total amount of energy is constant, so it's going to be equals to, so 1/2 m, and then I have an amplitude here, square, because it's square, so that's going to be this square, omega square, sine square, blah, blah, blah. Okay? But you know that omega square is, in that case here, it's going to be K. It's going to be K over M. So kinetic energy equals 1/2 the mass, A square. And then here it's going to be K over M, sine square, blah, blah, blah. So that goes away. And you are left with 1/2, and then you have an A square, and you have a K, and you have a sine square, blah, blah, blah. So for the elastic potential energy is 1/2 kx square. So the potential energy, elastic potential energy is 1/2, and then you have a K, and then you have a square, cosine square, blah, blah, blah. Okay? So when you add them up, when you add kinetic at a given time and potential at that given time, so if you add this here, this plus that, so K plus K, which is the kinetic energy plus the potential energy, you're going to get what? 1/2 K square, and then you have cosine square, blah, 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 plus sine square, blah, 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 and this is 1. So what do you get? At any time, the total amount of energy equals 1/2 kx square. We already knew that. We did a lot of problems using this. Okay? So that means that the total amount of mechanical energy equals 1/2 kx square. So that's in that case here, when everything is in the spring, stored inside that spring here, which is the same as 1/2 mv max square, which is equals to 1/2 kx square plus at a given time plus 1/2 mv square. Okay, so the total amount of energy stays the same, and using this new expression, of that expression, you can show that. Okay? So when you find the kinetic energy or the elastic potential energy, you see you have a cosine square and you have a sine square. Okay, so the sine square will be the kinetic energy. That will be your sine square. And the potential energy, elastic potential energy will be sine square. And you see how when one is maximum, the other one is zero. When this one is zero, that one is maximum. So you see again, the elastic potential energy looks like a quadratic equation here. You see how it goes from maximum to zero to maximum again. And you see that when it has that much of elastic potential energy, the rest of the energy will be kinetic energy. But we already discussed that. Okay, so here again is the same thing. Energy will goes up and down as a sine and a cosine function, except it will be positive. Okay, so again, you have one which is a cosine square, the other one which is a sine square. And they are always out of phase. When one is maximum, the other one is zero. Okay, so energy is transferred back and forth between kinetic and potential forms. So that is if there is no damping, that is if the only force involved is the restoring force. So if you do have damping, okay, so then we call that motion damped harmonic motion. So that means, for example, you don't want your car to jump up and down like the old car. So you're going to introduce some damping here. I'm just making sure that I'm not forgetting anything. So about damping, you see, you have different kinds of damping. And here that picture comes from a video that I recommend. So let's see if I can find the video for you. Not this one, this one. So I hope I'm not going to be in trouble if I show you this video in my video. It's a very nice channel. It's called The Efficient Engineer. And this video is very nice to understand again with an engineer point of view, the resonance and the vibration. But you see here you have a system, you have a mass and you have a spring. And here you introduce some damping, okay, with a fluid.
Each successive oscillation will decrease until it stops.
So you see how the oscillation, they don't keep going forever because you have some
if the damping of the system is increased significantly, which you can think of as the dash pot being filled with a far more viscous fluid, any oscillation will be completely suppressed by the damping. This is called an overdamped system.
Okay, so you have different kinds of damping. So if you have just a little bit of damping, you're gonna still keep the same frequency, okay, which is called the natural frequency. So it's still gonna oscillate with the same frequency as before when there is no damping, but you see that the amplitude is gonna decrease. So in that case, you still have the same cosine function or sine, but it will be inside the envelope here. So it means it will look like this. So it will still oscillate with the same natural frequency. So you still have a cosine here, but the amplitude here will decrease exponentially. So you will have this expression. So how do we get this solution? That's not out of the scope of this video, of this class. You have to solve that differential equation here. So you have the same differential equation as before. So you have MA equals the force which is the restoring force, minus kx. But now you add the force of friction because of the fluid. Okay, we suppose this is a friction due to fluid, so like air. So that will be air resistance, for example. And you see that air resistance in that case depends on the velocity. So it's very much like something is falling from a building. As it's going to move faster, the air resistance is going to increase. And that object, like you open a parachute, for example, you have air resistance that will push, that will slow you down. And that air resistance will increase with the speed at which you are falling. So here the same thing. So you introduce here a force of friction that will slow down the mass. And if it's not too much, okay, so it's called weak damping. So the oscillations still occur at the same frequency, but you see the amplitude is going to decrease exponentially. So you're going to have this expression there. Now, if it's overdamped, it's going to stop right away. Okay. So you can have critically damped boom or overdamped C. But again, this is not in the scope of that video. But it's a nice simulation here that you have.
And a critically damped system occurs right at the limit between these two cases. It is just enough damping to suppress vibration. Each of these cases has a different function that oscillates. A parameter called the logarithmic decrement can be calculated based on this test data as the natural logarithm of the ratio of any two successive amplitudes.
So you can watch that video here. Okay, so most interesting thing. So here again, here the same thing. You can have a simple harmonic motion. So it means it will oscillate forever and there is no damping. You can have a situation where it's underdamped. So it will be the green or the yellow. And you still have the same frequency, but the amplitude will decrease. And then you have critically damped or overdamped. So what you see is that all the system that all those oscillators like this one, right? You just pull on it and then you let it oscillate on its own. So all those oscillators have their own frequency. They call that the natural frequency. Okay, they want to oscillate at their own. It's called the resonance frequency. So here you have like a spring oscillating back and forth, but it could be anything that will oscillate. So for example, I have another example here.
When any stable mechanical system is disturbed, nature's response is simple harmonic motion. For a single oscillator, that's as far as it goes.
So here I have a simple oscillator. I let go and it will oscillate on its own, right? So it will have its own natural frequency.
That's as far as it goes. But when oscillating...
So this is called the resonance frequency. So for example, if a child here, it will find its own frequency, right? And this is called the natural frequency. You excite once and then you let go. It will oscillate with its own frequency. If you have, for example, if you walk and you let your arms swing back and forth, after a while, it will want to swing at its own natural frequency. Back in the 70s in France, we had this very famous car. It's called De Chevaux. It's by Citroën, so it's a very famous brand in France. And they were very cheap car, very popular. And they were very known. They were known because as soon as you went over a little bump here, it will start to oscillate like crazy. That was the natural frequency of the car. You have also falling in love, for example. This is also like emotional resonance, right? You have a small input, you have a big output. If you talk to your friend about a specific issue and your friend is very sensitive about this issue, especially today, then your friend will go off the roof because you just touch on that resonance frequency. Okay. So any oscillator has its own natural frequency. So here I have you have those slab here, you let go and it will oscillate with its own natural frequency that we can find using the mass and K. The pendulum will swing back and forth with its own natural frequency. And here, for example, I have also an oscillator. I can pull on it like this. I let go and you see it has its own frequency. The frequency will depend on the tension on the string, the length of the string, but it will, or if it's a spring, it will depend on the K and the mass. So it will oscillate back and forth. Now, instead of doing this, I can pull like this, and it becomes a simple harmonic oscillator, and it has its own natural frequency. So in that case, it depends on K and the mass. And we've seen, by the way, that K depends also on the length of the spring. But that's not what matters. What matters is that this is an oscillator and it has its natural frequency. So now we have what is called driven harmonic motion. So it means you don't let go. That means that you don't let go. So you grab your oscillator and you start to drive the oscillation. What's going to happen? So you're going to force on the oscillator the frequency that you want. So it means, for example, if I grab someone and I start to shake that person, okay, if I'm strong enough, I'm going to shake that person. After a while, that person is going to shake at the frequency that I'm forcing on that person, right? So this is called a driven oscillation. So what's going to happen with those driven oscillation is that if I happen to shake the oscillator at its own natural frequency, that's when you have resonance. And I'm going to show you a lot of examples, but let's do a little bit of math, not too much. So let's see what's going to happen. So it means, for example, let me show you an example. I have a wave on a spring. I have a string here, and I'm gonna drive it. Okay, so I'm gonna drive it. I'm gonna have a driver here, and I'm gonna force the oscillator. I'm going to force the oscillator to oscillate at my frequency, the frequency of the driver, right? So what's going to happen? So that means I take my oscillator, so maybe it's going to be an oscillator like this. And instead of letting oscillate at its natural frequency, okay, I'm going to I'm going to drive it. So I'm going to grab it here with my hand. I'm going to push and pull at a given frequency. Okay, so it's going to be driven oscillation. So I'm driving the oscillation and the frequency will be omega. So I don't let that oscillate back and forth on its own. Or you could do something like this. You can do, you still have your mass here and here. And now I am driving it up and down. So I force it to oscillate up and down. Its natural frequency was omega. So I pull and push in this direction with a driven frequency omega. So let's look at Newton's second law. So F, the net force, is going to be MA. Okay, so nothing new here. But the net force now is still going to be, so I forgot to show you that slide here. So maybe you have a better understanding here. So I have a vertical oscillator. I'm going to drive the oscillator up and down, up and down. So I'm applying a force, but that force will change with time. Okay, it has its own frequency, driven frequency, right? So I'm going to write down F equals ma. So you see that's ma, the acceleration. This is the acceleration equals to the net force. So the forces here will be the restoring force from the spring. It will be the frictional force from air resistance, and then it will be me driving the oscillator. So we're going to forget about damping here. Okay, so it will make things more complicated. And it's not it's just math. It's not that hard. But let's forget about damping here. Let's see what's going to happen. So I have F equals ma. So again, here I have my spring and I grab it here and I shake it up and down with a frequency omega, and this is the resonance frequency. So the solution, so first of all, the Newton's second law, F net equals ma. So you have the restoring force minus kx, plus you have the driving force, right? So the amplitude is, it's a force, right? The amplitude is maximum force that you apply. And then here it's going to be cosine omega t, right? Equals the mass times the acceleration along the x. And I'm going to call that x. So when the acceleration is this way, when it's going that way, acceleration this way, the restoring force is opposite direction. That's why you have a minus k. So if you shake it after a while, so you have to wait for the system to settle down. So it's called the transient. After the transient phase, you wait for a little bit, and then that oscillator will be driven at the same frequency than the driver. So it's going to be, the solution will be something like this. Solution will be, it will be driven with an amplitude A, but with the same frequency as the driver, right? So it means if you shake someone like this, at some point, you know, that person will shake at the same frequency that you are pushing and pulling. Okay, so we want to find what is A, and we plug that into that equation. So it's going to be minus K, so A cosine omega t, and then I have the force here, the amplitude of the force cosine omega t equals the mass. And then here I have to derive 2 times. So I'm going to have a minus A omega square. and then I have a cosine omega t again. So you can cross out the cosine here, and you have the force sub-zero equals k times a, and then I have a minus, I have an m, I have an a, and I have an omega square. K, so remember omega 0 squared equals k over m. So k is omega 0 squared times m. I don't want a k because I want the equation to be true for any type of simple harmonic oscillator. So I want to remove that k here. So it's going to be f sub 0 equals, I'm going to have, so k, omega 0 square m, then you have the amplitude minus a omega square. So what do we get? We get that the f sub 0 equals, you factor out the amplitude, and then you have omega square minus omega sub 0 square minus omega, and then you have the mass, here. Okay, so the amplitude equals the driving force. Here you have the mass of the system over omega sub 0 minus omega square. So the final solution is that the response, so it's like you have input, so that's your system, that's your oscillator. This is your simple harmonic oscillator. The input is f sub 0 cosine omega t. So you shake your oscillator at your frequency. You force that frequency on it. The oscillator is going to oscillate, but its amplitude will depend on, of course, that amplitude here, but also omega sub 0, its own natural frequency. So this is your input, that's going to be the output. So the output is going to be, f sub 0 m Okay, so the output is going to be f sub 0 m. Of course, it depends on the mass. If it has a lot of inertia, then it's going to be hard to get the right amplitude, to increase the amplitude. And here, you see, it depends on the natural frequency. Okay, so that's what happens if you take a simple oscillator and you start to shake it. Now, if you look at the graph, so let's look back at my slide here. So you forget about damping. If you forget about damping, that's what you're going to get. That will be the amplitude that you get, right? If there is damping, then you need to add a term here. There will be always damping, but to understand the resonance, let's forget about damping. But you see, it's just a little term that you need to add here. Now, if you look at the amplitude as a function of omega, so if you look at this amplitude here, you see there is a dependence here in omega, the driven frequency. And if you look at the amplitude here as a function of omega, what you get here, you have the natural frequency. And if there is no damping, but there is always damping, you see that when omega equals 0, so the amplitude will be equals to f sub 0 over k. Okay, so because then you get m f sub 0 divided by m times omega 0 square, m times omega 0 square, which is k. And then you see when the driven frequency equals to the natural frequency, ooh, it's infinite response, so infinite output. And here, then it will get to 0. It will get something to 0. Okay, so it's negative here because there is a business of phase shift, but you don't worry about it. So the thing that you have to understand is that you have resonance here. So it means if you shake something at its own natural frequency, the output can be devastating, right? It will be a catastrophe. So for example, if you have an earthquake and the earthquake start to shake the building at their own natural frequency, that's when the building is going to collapse. And the natural frequency will depend on the height of the building. So I'm going to show you a video about that. So if there is no damping, you see the amplitude can be very, very, very high. And that graph here will be very narrow. If you have a lot of damping, that won't be that bad. So I'm going to show you videos that I have just to show you what resonance is. So anyway, this is resonance. It's when you excite a system, when you drive a system at its own resonance frequency, at its own natural frequency, the response can be very large. So let's look at videos that I have for you. So for example, okay, so this short video comes from a series called Mechanical Universe. You can find this series on YouTube. It was a very nice series. It's an old one, but it's also very nice.
Having an oscillator of natural frequency omega naught causes complicated but tiny vibrations. At higher frequency, the vibrations get a little bigger. But if omega gets close to omega naught, then even if the size of the force is very small, some pretty spectacular things can start to happen.
So this is the oscillator that you start to drive, right? And if you drive it at its natural
added to the natural motion, a low-frequency force has its effect.
So that's the driver, right? This is F sub 0, so you are not driving very far, just up and down, up and down. But if you hit that frequency, the response will be very large. So small input, large output. So we are here.
At higher frequency, the effect can be more interesting.
So do you see you are not changing the amplitude of the force, right? You are just changing the frequency at which you are shaking the oscillator, and you are getting very close to the natural frequency. So it's going to go higher, the amplitude is going to get higher.
But if omega gets close to omega naught, the effect can be positively shattering.
You see, a small input will and the output will be very large. So small input, large output at resonance. So let's look at some example. So that's let's look at this one. First, you have to be careful with your ears. It's a very annoying video. See, I told you, I'm gonna decrease the sound. So you have a glass here, it's a crystal glass. And you see glass is an elastic material. Okay, over a very long time, it can even flow. If you go to Europe, for example, very old building, you see the window, you're gonna have a thicker window glass at the bottom that you have at the top because it can flow, right? So glass can be changed. That can change the shape. Okay, it can oscillate. So here you have a driver, which is a sound. So you have a sound wave that's going to push and pull and push and pull the glass. And at the right frequency, as you increase the, you're gonna look for the frequency, resonance frequency. When you hit the resonance frequency, you're gonna see what's gonna happen. It's being shattered. So it means for a small input, the amplitude is not that big. You can have a large output as long as you are driving the oscillation at the right frequency. So they say that very good singer, like especially women, like so I don't know if it's true or not, but I think it's true. Ella Fitzgerald, very famous singer, very good singer. And so if you have a very good singer, they could listen to the resonance frequency of a glass, right? They will just go around the glass like this and they can listen to the resonance frequency. And then if they match that frequency with their voice and enough amplitude, then they can shatter the glass. So this is Ella Fitzgerald.
Can the amplified voice of Ella Fitzgerald shatter this glass? Believe it. Ella Fitzgerald on Memorex cassette tape.
So that was an old commercial to show you that tape here is so well done that it can also shatter the glass. So then you won't be able to tell the difference between the real Ella Fitzgerald and the tape.
With MRX2 oxide, can Memorex shatter the glass? Now we ask, is it live or is it Memorex?
So very famous commercial, great singer here. So this is just for fun. So what happened? What do you think happened? So I think it's commercial from Brazil and it didn't shatter. So how come it didn't shatter? So I always ask that question to the student. And you see why, because it was made of plastic. So even if it oscillates, it doesn't break like glass. Okay, so resonance can be dramatic. So this is a very famous example that engineers have to study in civil engineering. It happened in Washington State. They just had, I think it was in the 1940s. It's called the Tacoma Bridge. So they just finished building a nice bridge. And then the wind started to push and pull back and forth the bridge, but it was pushing and pulling at the own natural frequency of the bridge, and then the bridge collapsed. because of resonance. So very famous story. You see how it's swinging back and forth? So everyone was asked to leave the bridge. There is one professor who forgot his dog in the car, so he came back to get the car. So that's the car here, and you walk on the bridge to get the car, to get the dog. So he saved the dog's life. And then everything collapsed, right? So it's a very famous example of resonance. It's called the Tacoma Bridge. You can look it up. You can find the video on YouTube. So since then, what they do now, they make a model of the bridge, and they try that bridge with a wind tunnel. So they want to make sure that it will resist the wind at any frequency. So it was very unlucky that the wind was pushing and pulling with the same natural frequency as the bridge. So it's a school example, right? It's a very famous example. So let's look at other example. Talking about earthquakes, interesting. So you see, you can model building here. So you have the mass. So the mass is always important because that's the inertia, and different building will have different length. So the earthquake comes and it's going to shake the building at a given frequency. If the frequency of the earthquake, so it means the driven frequency, match the natural frequency of the building will collapse. That's what he's explaining here.
Y el periodo está en función de dos cosas, de la rigidez del elemento, en este caso la solera, y de la masa. Este es un piso y esto es una columna. Entonces, los periodos varían en función
so that's
de la
the
masa.
Natural frequency.
Periodo,
and you see they all have different frequency. The shorter
y
one have a higher natural
si
frequency. It's very much like a pendulum, right? A pendulum upside down.
Es una casa en las lomas,
so short building, higher frequency.
Y estos son unos
Long
edificios
building,
que tienen más rigidez,
low
y uno de ellos tiene
frequency.
amortiguador. Si yo los excito, ¿de acuerdo? Este que tiene un amortiguamiento se para rápidamente y este sigue vibrando.
Está buenísima la explicación.
Entonces, si yo quiero tirar un edificio en la colonia Roma,
So now
lo
there is an
lo
earthquake
excito
coming.
con las aceleraciones de la colonia Roma, que son como 2 segundos. Entonces hago esto. Vean los
So
edificios que se
some
excitan en la
building
colonia
will not
Roma.
respond
¿De
at
acuerdo? Los
all.
que
Some
coinciden con
building
la
will
forma de
respond
moverse del
because
suelo. Las casas de la
it has a
las-
low
no les pasa
frequency.
nada.
So only the
Si yo
tall
quiero
building will
perjudicar a los ricos
respond.
de las lomas,
Now if
lo
you
hago
go
con un periodo
faster,
muy corto y hago esto.
this one will
Y los
respond.
edificios altos no se afectan
So
los
you have
edificios
to
que tienen
be
periodos cortos.
aware of that to
Esa es
build
la idea, esa es la dinámica de las
when you build the
estructuras. Entonces, lo
buildings.
prudente es que los edificios no se muevan como el suelo.
I think there is another nice one here. So now that's
Here I have in this demonstration.
so you have different oscillators. So the short one will move faster, so they have a higher natural frequency. The long one have a larger natural frequency. So when you excite this one, the one that will respond will be this one, because they both have the same natural frequency. And this is video come from Pearson. I think it's from the book Wolfson, Fundamental of Physics.
4 sets of rods of different lengths, and they're all connected by this steel base. Now, the question is, if I pluck this large rod, how will the other rods respond? Will they all start to vibrate? Will the vibrations be different depending on the length, or will just the matching rod vibrate? So as you can see, when I pluck this one, the matching rod starts to vibrate while the rest remain steady. This is because when I set this into oscillation and sent vibrations through the base of a certain frequency, the frequency of this rod, which was picked up by this rod since it has the same natural frequency as this one, and started to vibrate. The rest of these rods have different natural frequencies, which are not equal to the frequencies of these rods, and therefore they did not vibrate. Here I have
same idea. You can do that with tuning fork. Okay, so first of all, you have a tuning fork here. A tuning fork is also a simple harmonic oscillator. So it will oscillate in this fashion. So it's going to push and pull air. So it makes like a sound wave. It will make a sound wave. Sound wave is when the air is squeezed, stretch out, squeeze, stretch out, squeezed, right? So it's a simple harmonic oscillator, and it wants to oscillate at that frequency. So this is its natural frequency, 512 hertz. And you see that it's attached to a box here. So it will, what it does, it will make the air inside that box here vibrate at the same frequency. So it will amplify the sound. Otherwise, it's very hard to hear the sound. You have to put your ear very close to it. So here you have another fork here, tuning fork, and it does not have the same frequency, so it should not oscillate. So nothing here. So now it has the same frequency, 440 hertz, 440 hertz. So this one should be set in vibration because they have the same natural frequency. You see, the air sound wave is making those masses vibrate at the same frequency. Okay, I think that's very cool. There is another one here, and that will be my last video. It's telling the same principle. Okay, so they have the same frequency. There is a box here, so air will vibrate, and then it's easier to hear with a microphone. You stop, you put your microphone here, and you can hear it. Isn't that cool? I think I show you everything I wanted to show you. Okay, so next time we'll talk about standing waves. I hope it was not a too long video.